Okay, welcome everyone to our Institute for Quantum Studies seminar this week. We're very happy to have Mark Srednicki come and give us our seminar. So Mark has a very distinguished career in physics. He did his PhD with Lenny Susskind in Stanford, and he's worked on many things over his career. He started out as a field theorist and continued to work in this area. In fact, has a magnificent textbook about quantum field theory in 3 volumes that he's written. He worked in quantum chaos, and he told us about his work in statistical mechanics. He's also done some work in string theory and foundations of quantum mechanics, so he has many interests. And he also has a number of students, so one of whom is me.
This is my greatest accomplishment.
So we're really happy to have Mark make the drive down from UCSB. And now that you're retired, Mark,
Yes.
you have an open invitation. Anytime you feel like you need a little bit more sunshine from Santa Barbara, you come down to Orange County, we'll take care of you. So the floor is yours.
All right. Well, thank you. Yeah. So as Andrew mentioned, I started out as a high energy particle theorist, but then I got interested in this topic, and so most of what I'm going to tell you today is actually now quite old. It's dating from the 90s, but I think it's not well known, and I think it ties into stuff people here are interested in. So I'm hoping it will be of sufficient interest to you all. The question I want to start with. Why is this not working? There we go. Okay, so again, I was doing particle theory, and then I somehow got assigned to teach statistical mechanics. Apparently, the usual suspects were not available, and but I thought, okay, this is good. I will. I was excited about it, and I thought. I had this pedagogical idea that the first thing I would do is explain that if you wanted to get the standard results of statistical mechanics, but you didn't actually know statistical mechanics, it was quite complicated. And that's why we should all know and use statistical mechanics. And so I started thinking about this sort of classic problem. We have a box with some atoms of a gas in it, and they're going to start out, they're going to start out, say, in the lower left corner moving up, and then we know that a little bit of time later, they will have moved out and filled the volume of the box, and they will be zooming around in different directions with a Boltzmann distribution. Okay, so I started thinking about how would we deduce that this happens, starting from just ordinary physics. And if we were going to use classical mechanics to describe the system, I had some vague idea about how this should work. And we know what happens. They hit each other, they bounce off, they zoom around. And I knew some words like ergodicity and chaos. And I thought, yeah, I probably understand, I could probably go fill that in. But coming out of particle theory, where everything is quantum mechanics, I, of course, wanted to do the problem quantum mechanically. So I wanted to start off with the gas on the left. I wanted to put these in little Gaussian wave packets, and then time evolve the whole thing with the Schrodinger equation. And then see that later I got a quantum state that was at least compatible with the picture on the right. And so I started thinking about, well, how would I actually show this from quantum mechanics? And I slowly realized that I had no idea how to do that. And then I thought, okay, I must have skipped class the day they explained it. So I went to the library and I started pulling all these books off the shelves. And I discovered that the books all said stuff that I did not find convincing. And I was annoyed by this. annoyed enough to keep thinking about it for a long time. And then it came time to teach the class, and I was still confused. So I told the usual hand-waving stuff to the class, and then kept thinking about it. And eventually I came up with some results from quantum chaos theory, because I had this vague idea that chaos had something to do with it in classical mechanics. And I vaguely knew that there was something called quantum chaos. And so maybe that was relevant. And so I started reading quantum chaos papers, and I discovered first, that was a really interesting topic. There was lots of very interesting stuff there. And second, the quantum chaos people actually did know some things that properly reinterpreted could be used to explain this. So that's the story I'm going to tell you today. Okay, so we're going to have to, well, I don't have to, but I'm going to start out by setting up some assumptions. So and again, I'm going to be doing everything quantum mechanically.
Mark, can I?
Yeah.
How satisfied are you now with your understanding?
Very satisfied.
Wow, great.
And furthermore, other people are now convinced too. So
Nice.
This is the thing that's happened over the last couple of decades. So, okay. So we're going to have a quantum mechanical system, and I'm not going to be very precise about it. If you want to think about something precise, we can think about that gas. We can think of it as a gas of hard spheres. But we could also think about spin systems like Ising type models or Heisenberg type models. A key assumption is there will be many degrees of freedom. So I'm going to have some number n that stands for the number of degrees of freedom, loosely defined at, factors of 2 or 3. Do we call the gas of n spheres in 3 dimensions? Is n or 3n? That's not going to matter. N is just some number that characterizes the number of degrees of freedom. Then we're going to have some set of observables, because in a real experiment, you of course cannot observe everything. You can observe at most some finite number of observables. And so, for example, in the hard sphere gas, we might count the number of particles that have a certain momentum, or momentum in some range. And so this index I call observables A for no particular reason. And the index I just tells us which one we're talking about, although most of the time we'll just need to talk about one at a time. But it's important that we have a set of observables and that they are somehow physically relevant. I'm not going to let you make up an observable where you just write down some matrix in some basis. It has to have some physical connection. Okay, and then we have some quantum state, which I will take to be a pure state. We could also talk about mixed states, but the tension between quantum mechanics and conventional statistical mechanics is strongest for pure states, so we'll focus on pure states for that reason. And then the quantities that I'm going to focus on are the instantaneous expectation values of these observables. Now, of course, an expectation value does not carry the full set of information. However, we could, if you also cared about fluctuations in time around the expectation value, you could look at the expectation value of the square of the observable, or even higher moments. So I would allow you to put those on your list of observables. So we could, okay. All right. Okay, there we go. All right. Now the system will have some expected total energy, which is just the expectation value of the Hamiltonian. And I'm going to assume that this scales like the number of degrees of freedom, so that I have a finite energy density, which in statistical mechanics language would mean a finite temperature in the thermodynamic limit. I don't want to be very close to the ground state. So I want to be some distance above the ground state, which in conventional stat mech language would be a non-zero temperature. There will also be, unless the state is an exact energy eigenstate, there will be some quantum uncertainty in the energy given by the standard textbook formula. And this I want to assume is small. And I will say that it's small by saying it scales like n to some power that's less than 1. So that, again, I want to think about n being large, but I don't want to take n all the way to infinity, because if you take n all the way to infinity, then you have to decide what you're holding fixed and so on. So it's just easier to think about n as large but finite. Okay. And then for comparison, we'll need some thermal stuff. So I'm going to define the canonical thermal expectation value in this somewhat unusual notation, but with a conventional formula for it. And to write this down, I need to know what this inverse temperature beta is. Beta will be fixed by saying that the thermal expectation value of the Hamiltonian is this energy, which we actually get from the exact quantum state. And then if you computed delta E using thermal expectation values, for that case, gamma is 1/2. So it's perfectly reasonable to have delta E be small in that sense, that it scales like a power of n that's less. Okay. And these are some restrictions on the state. I'm not allowing complete arbitrary. I guess I should back up a bit and say the goal is to try to put as few restrictions as possible on the state. I want to get StatMech out without, I want maximum freedom in choosing the initial state. But I do want the energy to be, first of all, to scale like the number of degrees of freedom, and second of all, to have a quantum uncertainty that's small. Okay. Now we need a definition of thermal equilibrium, because one thing I discovered in the early days of this is that I could have long conversations and then eventually realize that the person I was talking to was using a different definition of thermal equilibrium than I am. So my definition of thermal equilibrium is, first of all, time dependent. We will say that the state is in thermal equilibrium, the system is in thermal equilibrium at time t if this quantum expectation value is equal to the thermal expectation value within some tolerance. We can't expect million decimal place equality. So within some tolerance, which would at least be something like 1/n, because even in different thermal ensembles will differ in their expectation values by 1/n. So something like that. We're not going to need to be very precise about this. And that this should be true for each of the observables we put on our list. So thermal equilibrium in this sense is both time dependent. If all the air in the room was to spontaneously move into the corner, I don't want to say that that is now a state of thermal equilibrium of the air, even though it just did it spontaneously. So if a system spontaneously does something so that it no longer looks like anything anyone would call thermal equilibrium, we're going to say it's not in thermal equilibrium. And it also depends on the set of observables we've chosen. And again, this is supposed to be a caricature of a real world situation. If I go to a graduate student and say, here's a box of gas, tell me whether this gas is in thermal equilibrium or not. What is the poor graduate student going to do? I stick some thermometers into it in various places, and if all the thermometers give the same answer, they will say, yes, it's in thermal equilibrium. So what they've done is measure the momentum of the particles near the thermometer. Okay, so that's some set of observables. It's not every observable, and for all they know, maybe the temperature would have been different. The first 10 thermometers gave the same temperature, but maybe the 11th thermometer didn't, but they don't know. Okay, so we call that thermal equilibrium. Okay, so the definition is both time dependent and dependent on what we choose to measure, but I claim this is all actually what happens in real measurements.
Mark, are you excluding the generation?
Sorry,
Suppose that it is more complex system.
yeah,
That in thermal equilibrium, you can have many degenerate state with many, how to say, many different states with the same thermal energy.
yeah, no, there are, yeah, so this definition says if whatever the state is, if if it satisfies these criteria,
So it's uniquely defined, or not?
it's not going to uniquely pick out a state. No, there'll be many.
So you can have the generation.
Yeah. Okay. So what do we expect to happen? So this again is supposed to be some caricature of the box of gas. I started let's suppose that our observable A counts the number of particles with some momentum P, and suppose momentum P was the up momentum that we started with. So we start with a big excess of particles of momentum P. But then as the gas, time evolves, we have this picture of the molecules, atoms, wherever they are, knocking each other around. And so the number with this particular momentum will go down and eventually come down to the thermal expectation value of that energy. And here this is an artist's conception. I've drawn the line somewhat jagged because we expect fluctuations. Okay. And then after this, we expect it to stay here most of the time with some fluctuations. And maybe occasionally there'll be a big fluctuation, but those should be rare. That's what we expect to happen because we did take the class in StatMac.
Boltzmann, right?
Yeah, or I've actually read Boltzmann's books. I recommend, although Boltzmann, he spends a huge amount of time in his book arguing that an integral is a sufficiently good approximation to a sum. Because he's worried about this. You can skip that part. All right, okay. So what I want to do is I want to ask, can we get this picture from quantum mechanics without putting any more restrictions than the mild restrictions we already had on the state? Okay, so I'm going to imagine that my system occupies a finite volume and therefore has discrete energy eigenstates. So there are discrete energy eigenvalues. Time evolution will be the standard time evolution of an isolated system. And I'm betraying my high energy theory roots by leaving out the H bar here, setting H bar to 1. Okay, now we can just write down a formula for this expectation value just by plugging this in. And I'm going to break it up into 2 parts, a diagonal part here and an off diagonal part here. And again, here is the picture. And what we want to try to understand is, under what circumstances will this formula give us this picture? We believe the formula because we took the class in quantum mechanics, and we believe the picture because we took the class in StatMac, so they should be compatible. Okay. So the first thing one could try thinking about is and I gave away the secret. Touching my key. Yeah, so if we time average the formula over a very long time, and it has to be a very long time because these energy eigenvalues are very closely spaced, they're exponentially close together. So I need to time average for an exponentially long time to kill all these phases. Which I can do because I'm a theorist. So this time averaging has nothing to do with a time average in some experiment that you do over some reasonably short time. This is the theorist time average, which is, e to the n years. I can also time average the picture. Okay. If I time average the formula, I get this term. If I time average the picture, I get the thermal expectation value. And so therefore, these two things, if the formula agrees with the picture, should be the same. And the other part will give us all the quote fluctuations, including thinking of this initial thing as a fluctuation, just any deviation. Okay, and the first puzzle is this equality. How can this be true? The problem here is that this thermal expectation value knows almost nothing about the state. The only thing it knows is the total energy. Whereas this quantum diagonal piece seems to know a lot about the initial state. It's got all these C alpha squareds in it. Okay, so how can these possibly be equal? And one way they can be equal, and pretty much the only way they can be equal if we don't place any restrictions on the C's, is if the A alpha alphas look like this. If I plot these diagonal matrix elements as a function of energy, I want them to lie on what looks like a smooth curve. I'm just pulling this out of a hat. I'm just saying, let's suppose this is true. No justification at this point at all. Just suppose it's true. If we suppose it's true, I now want to plot the C alpha squareds, and somehow I've lost my.
And what are these red dots?
Yeah, somehow my caption disappeared. The red dots are the C alpha squareds. So, and the C alpha squareds are allowed to jump around. But they're supposed to be, remember, we've assumed the state has some quantum uncertainty, which is relatively small. So these should span a relatively small range. Okay. And now to get this expectation value, or the diagonal part of the expectation value, we multiply the red dots by the blue dots and add them up. But because the blue dots basically have the same value throughout the range where the red dots are varying, it doesn't matter what the red dots do. We're going to get, if we project onto the left here, we're going to get 4.5 or something, plus or minus something. Okay. That has to do with the uncertainty in the energy. But again, just different statistical ensembles will give you the same sort of energy. Same sort of variation. So if by some miracle, these diagonal matrix elements lie along a smooth curve, then it's not going to matter what the C alpha squareds are, and the diagonal term will be the same. So if A alpha alpha varies smoothly with alpha and delta E is suitably small, then the details don't matter, and this sum depends only on the total energy, because what the total energy is tells you where you are along that smooth curve. Okay. And then a slightly more subtle punchline is that whatever you get, that will also be the thermal expectation value, because the thermal expectation value satisfies this condition. The thermal state has a small delta E. Now, it's not very clear compared to this curve, because the C alpha squareds for Boltzmann weights are just falling exponentially. But this curve is bad in that I've drawn all the blue dots as equally spaced, but in fact, they're getting much more tighter space because the density of states is rising exponentially. And so when you combine the exponential falling of the weights with the exponential rise of density of states, you end up with a small delta E. Anyway, okay. So this picture doesn't really apply to that situation, but the math does. And so once you know that this only depends on E, then it must be the thermal average, because I could have used Boltzmann weights for my C alphas.
I'm sorry, one question. So
yeah,
I think, smoothly is not enough, is it? I mean, you mean real analytic or so, right?
Well, they're discrete. So what I really mean is that if you compare two neighboring ones,
right, okay,
put some bound on the deviation.
Okay, no, that's great. But that's okay. Yes, that's great. Thank you.
So you should compare red with blue.
Sorry?
Red with blue to see which one is smooth, which one is sharp.
Yeah, yeah. The blue are smooth, the red is sharp.
That is
But the
the
red-
criterion.
Yeah, that's the only criterion. Okay, all right, and I coined a phrase for this called eigenstate thermalization in a paper I wrote in 1994. It then turned out there was an earlier paper by Josh Deutsch in 1991, which said something very similar. And if you dig, and there's a very nice review from a few years ago by these folks. And if you dig through the old literature, you can find many papers that said things that were sort of like this, usually in the context of some specific system. So some version of it was known. Okay, but all right, so coming back to this, I claim we've now, this part, that the diagonal piece should be the thermal value, which is naively paradoxical, because this looks like it depends on the details of the state, and this looks like it doesn't. That's okay if these diagonal matrix elements vary smoothly. Yes.
So if I remember, you defined the temperature beta in terms of the expectation value of the energy, right?
Yes.
So doesn't that include the definition, like the C alpha in the definition of beta itself?
It doesn't, no, because that definition of the thermal expectation value is right. That doesn't refer to the state at all. That's just the conventional canonical expectation value.
Right, but I was asking because you're finding the beta temperature from the equation H thermal equals to energy.
No, I'm finding beta from this, right? But this part only depends on, I mean, this is a very conventional definition, right? This definition holds in any StatMech textbook. So the bottom two lines here are all pure StatMech. I'm just defining, this formula is the standard thermodynamic relation between energy and temperature. So that's all it is. So and I'm assuming we're in a simple enough case that it's monotonic and all that.
In your hinge argument is that the expectation value E is not sensitive to the details of C alpha squared.
Right.
Therefore, that's why you can uniquely define it.
Yeah.
Okay.
Okay, and now we have to understand why there's another aspect of this picture, which is that the fluctuations are usually small. And we could define that by doing something like taking the difference between the actual quantum expectation value and thermal expectation value, squaring that and integrating over time, or averaging over time. That would involve things from this term. But without getting into that, all we really need is for these off-diagonal matrix elements to be suitably small, because whatever this is, it's some weighted average. I guess I never said the C alpha squared sum to 1 because it's the normalization state. So we have some order 1 weighting coefficients here. And if all of these are small, then this will usually be small. And the only way it can be big at some particular time is if we've carefully chosen the C alphas to make these line up as much as possible. But if we've done that at some time, as we did here at time 0, we chose a state where this expectation value is far from its thermal value, which we can do. There are C alphas we can choose that will make that happen. But then as time goes on, these phases will turn on, and that will mess up the alignment, and it will come back to. Okay. All right, so I needed these two conditions for my formula and picture to agree, that the diagonal elements vary smoothly with alpha and that the off-diagonal elements are small. And now we can ask, how reasonable is that? Because I got those conditions just by demanding that the formula agree with the picture. There wasn't any physics that went into that beyond that, no microphysics. And so happily, the answer is yes. And this is where the quantum chaos results come in. It turns out both these things are known to be true if you got your system by starting with a classically chaotic system and then quantizing it the usual way. So I'll go into that more in a minute, but this provides an example of systems where this is true. So it's not crazy to believe this is true. And we now think it's true you don't have to get your system by quantizing a classically chaotic system. If you have some sort of spin system in which you are far in parameter space from integrable systems, numerical results show that this is still true. But the sort of baseline example is classically chaotic systems. So ones that have been extensively studied are so-called billiard systems, where you just have a single particle bouncing around inside a shape. And so these are pictures of classical trajectories in two-dimensional billiards of various kinds, a square, an ellipse, a circle inside a square, which is called the Sinai billiard, a circle that's been cut in half and then separated by two straight segments, which is called the stadium billiard, and the cardioid billiard, which is a cardioid shape. And it has been proven that the classical motion in these bottom ones is chaotic. Which essentially means that there's no other conserved quantity. And then there are other things that follow from that, like exponential divergence in time of nearby trajectories and so on. So these are some nice pictures of trajectories by Arne Baker. And just looking at them, you can visually see the difference in the structure. Okay, but that is all classical. What happens quantum mechanically? So quantum mechanically, inside a billiard, it's just a free particle, so a plane wave is a solution. So I can try to make an energy eigenfunction by superposing plane waves in which the wave vectors all have the same length, because that's what's related to the energy. K squared is basically the energy up to some constants. But in which the direction of K is different. So I'm summing over a bunch of different directions of K, and I'm summing with some coefficients, C sub J. These C's have nothing to do with the previous C's. I just call everything C. Okay. And so, and in fact, this is one numerical technique for finding energy eigenfunctions in a billiard. You now want to choose the C's so that the wave function vanishes along the billiard boundary in position space. This is a momentum space circle. And that's one. And then there are numerical techniques to search for those C's. So that's one technique people use to find these energy eigenfunctions. And back in 1977, Michael Berry conjectured that before it was possible to actually do these computations numerically, he conjectured that if you did them, you would find that these C's look like Gaussian random numbers. The Gaussian part is not so important. Well, the important part is that they look random. And they, in particular, they look random from wave vector to nearby wave vector. They just jiggle around. And amazingly, this turns out to be true. So here again from Arndt is two pictures. On the left is a bunch of random waves superposed with coefficients he got from a random Gaussian random number generator. And on the right is an actual eigenfunction of the cardioid billiard, and with the same wavelength. Now, of course, the billiard has a vertical symmetry, so you can see the This is an even wave function that reflects around the horizontal line of symmetry. But while you're supposed to look at this, if you look at sort of the intermediate scale patterns, they look sort of the same. And of course, one can then also do various numerical tests and so on. And so here is a plot of a histogram of the amplitude of the wave function in position space. So he just pixelized and plotted it. And the prediction is that it's Gaussian. And you can see that it's Gaussian. In fact, it doesn't really show here, but there's under the blue histogram, there's a red dashed line. And so they're right on top of each other. And this is a no parameter fit because the wave function is normalized. It works extremely well. So Barry had a very prescient intuition, which he's had on many problems, but this is one of his more memorable ones. Okay, now that is for billiards. We can generalize Barry's conjecture beyond billiards. And more generally, what you find, I'm not going to go into details of this, but more generally, what you find is that if you have a wave function that's random in this sense, that you can break it down into some sort of basis functions, and the coefficients of the basis functions look like random numbers, that will lead to a uniform, smooth probability distribution over a constant energy surface in phase space. So again, going back to the picture, right? If there are these density wiggles here, but if I smooth it out, and the thickness of these lines is basically a wavelength. If I smooth it out on a scale large compared to the wavelength, then it's uniform in position space. And it's also uniform in momentum space because I'm superposing all these different directions. And so that's the general result. You get a uniform, suitably smooth on scales of the quantum wavelength probability distribution over a constant energy surface, which is just the classical microcanonical ensemble. And this, it turns out, is actually a theorem due to Alexander Schnirelmann. And I left the date off. I think it starts in 74. There are various technical assumptions that go into this, which have been steadily refined. And the quantum chaos people think of this in terms of powers of h bar. And the claim is that this diagonal expectation value goes over into a classical microcanonical average plus ordered corrections that go like the square root of h bar. Now, what that in practice means is you have to be at a high enough energy that you can think of the quantum wavelength as small compared to some classical length scales. Okay, and this is actually, we don't really need that it's the classical microcanonical average. All we really need is that the thing itself, it has a classical, it has something that the main term doesn't depend on h bar, and that it varies smoothly with the energy, which of course the classical microcanonical average does. But also so do all the quantum corrections. So in fact, the smoothness property is stronger than the theorem. Okay, but the punchline, the bottom line is we get this smoothness property of the diagonal matrix elements out of quantum chaos. So it is something in which we know a class of systems where this is true. It's not. Okay. We can also learn something about the off-diagonal matrix elements from the random wave conjecture. These off-diagonal matrix elements should vary I like the word erratically with the. If you say random, then sometimes random has some technical definition sometimes. So I don't want the technical, because of course you could compute them in principle, so they're not really random. Varies erratically because each of these wave functions has some different set of these Gaussian coefficients. Okay, and now we could compute something like the square of the deviation from the expected value. And if we insert a complete set of energy eigenstates, we will just get a sum of the off-diagonal matrix elements. This sum, if we tried to turn it, if we tried to make some sort of smooth approximation to these, the sum would contain a factor of e to the s, the density of states. So here I've introduced the notion of a thermodynamic entropy defined as the log of the density of states. So the density of states is e to the s. There's a density of states factor. I don't know why there's a bar there. I think there should really be the beta energy. But the point is, e to the s is a very big number. And s scales like n, so this is exponentially large in n. But this quantity, if this is some normal observable, this should be some order 1 thing. Well, if this is order 1 and this is huge and this is a positive thing, how can that happen? There are basically 2 ways it could happen. One way is most of these could be 0. This is what happens in certain integrable systems. The observable just doesn't change many quantum numbers, and so most of these are 0. In chaotic systems, and actually in a class of interesting systems called interacting integrable systems, where the integrable quantities are not simple, there's no reason for these to be 0. And if most of them are not 0, then they all must be very small. So that I can get this. So that's the conclusion. These off-diagonal elements are very small, which was the other thing I needed for the formula to agree. Okay. All right. These days, this is usually summarized in the following ansatz for matrix elements. This is now called I called the phenomenon eigenstate thermalization. Later, the word hypothesis got added to it. I didn't add hypothesis. I thought it was a fact. It's a hypothesis in that we can ask whether a system obeys it or not, because we can find systems that don't. But this now summarizes what I've been saying all along. Again, these are matrix elements in the energy eigenstate basis. There's a diagonal term which has a smooth function of the energy, and an off-diagonal term which has an e to the minus s over 2 suppression. Here now the energy is defined as the average of the 2 energy eigenstates. Then there's some envelope function that tells you how these things are varying, and this will be a function of both energies. It's useful to think of it as a function of the average energy and the energy difference. And the average energy we want, again, to scale like the number of degrees of freedom. But in most systems and observables of interest, we should think of the energy difference as scaling like order 1. And then there's some, quote, random, unquote, factor, which we should think of as something varying with 0 mean and unit variance, with the variance encoded in the sum. So this is now what people usually mean by the ETH ansatz for matrix elements. And again, empirically meaning via numerical investigations, it holds in systems like spin systems that don't necessarily have classical limits. So even though the part we can do with more rigorous math comes from quantizing classically chaotic systems, the physical criterion seems to be there aren't any conserved quantities other than energy, or a few that we can take into account in a way we similarly account for energy. Okay, so I wrote papers on this in the 90s, and basically no one cared until 2006, when David Weiss and his group at Penn State did a very interesting atomic physics experiment where they took 2 clouds of cold atoms in a laser trap, and the trap made them able to move basically only in one dimension. They were constrained by the lasers from moving in the perpendicular direction. And they put a very weak harmonic potential in the third direction, and they set up two clouds and let them collide and watch what happens. The naive thing is, well, they'll thermalize and form a single cloud. That's not what happens. What happens is they bounce off each other, or they go through each other. They're bosons, so those are the same thing. Here's a schematic of what's happening. Here's some of their actual data. You see the clouds come together and then come apart. I guess I'm supposed to read from top down. Okay, so they come together and then come apart, and then come together and come apart. So they're doing this. And they compared, this is from their paper, they compared this to what's called the Newton's cradle, this impact ball thing. These are really cool. When I was like 12 years old, these appeared as sort of novelty items, and I was totally fascinated by it. Made my parents drive around to like 10 stores trying to find one of these things, which we eventually
launched you on your physics career.
Yeah, well, yeah. That it came back in this way is kind of fun for me. So they called it a quantum Newton cradle, and this is what they saw. And actually, in this case, it's very easy to understand what's going on, because if it's really in one dimension and it's really two-body collisions, two particles in one dimension, if you collide them and conserve energy and momentum, all they can do is either go through each other or bounce off, and each gets its other's momentum. So there's no mechanism for changing the magnitude of the momentum. So there's no mechanism to other than, you know, simultaneous three-body collisions or, you know, whatever other imperfections there are. But the experiment was good enough that this two-body collision mechanism worked. But in the paper, they say, yeah, okay, we understand this, but, you know, still, what does that mean for StatMech? You know, we've done naive StatMech, we would have concluded we got one. This was then latched onto by some theorists, Marcos Riegel, Evangelos Dunko, and Maxime Olshani, who started what is now a more advanced field of numerical investigations of these kinds of problems. And so this was the thing they looked at. Hardcore bosons on an irregular lattice. Hardcore means you can only put one boson on a site at a time, and they had some interaction, but N here is just B dagger B, and they had some funky lattice where they put all the particles all on this side, and then at time 0, they turn on a gate to let you go to this side, and then they measured various things, measured in numerical sense. So this is the expectation value of a part. They had some strange observable, which is the Fourier transform of the number density, and this is the 0 mode of that. For some reason, they like this. And it starts out, the blue line is the actual quantum state given that initial state. And it then pretty quickly settles down into this red-green solid line, which is the microcanonical average. Now, they only had like 6 particles or something, so we're pretty far from a thermodynamic limit. And so actually the biggest deviation is the difference between microcanonical and canonical. Canonical is this purple line. What they call diagonal means this is the sum of the C alpha squareds A alpha alpha, just by hand throw away. And those things are all supposed to agree, and they do. And of course, if we were at more particles, we would get the canonical closer to the microcanonical. But the microcanonical is better at these small numbers. Okay, and this is now a comparison really of a whole bunch of different observables. They're now looking at different modes of this density, and they are comparing really microcanonical and 2 different energy eigenstates. And again, the prediction is that each A alpha alpha is the same, and that's what they find for all these different. Okay. So this was the first numerical verification of these ideas. All right, and then for comparison, they also did an integrable lattice where they have everything on a straight line with again, those interactions were nearest neighbor. And in a straight line, this turns out to be an integrable system, and you can find an infinite number, infinite number in an infinite slot on an infinite line, number of conserved quantities. Okay, and now this all fails, right? So these curves that all were on the same line in the quote chaotic unquote case. In this interval case, it doesn't work. They're all different, which is what you expect. Okay, so really that's my whole basic story. So what happened after that is, because now there are actual experiments, now people are interested. And so now there's a community of experimentalists and theorists who ask basically what systems thermalize, under what circumstances, so on and so forth. You know, the caveat to this is there are systems that don't obey this, that are not chaotic, that don't obey this eigenstate thermalization hypothesis. One of them is, again, as I've said several times, integrable systems with a bunch of conserved quantities. And that explains the Weiss-Newton's cradle result. Basically, all the individual momenta are conserved. And so the same group of people, adding another author, Jurovsky, came up with a general formula for this, which they call generalized Gibbs ensembles. Basically, instead of e to the minus beta h, you need e to the minus every conserved quantity times a temperature-like parameter, and then you can make predictions like that. Another large class of systems that don't obey this, on which there's been a huge amount of work, are many-body localized systems, where if you have sufficient disorder, this is Anderson localization, the way the energy eigenfunctions tend to get localized in position space. And then these clearly don't obey ETH because they're not spread out. ETH, okay. So, and now you can ask, well, how strong does disorder need to be? What happens at the transition? And so on and so forth. And there's a lot of work on these. And nevertheless, some of these systems will still thermalize for large classes of initial states, because I tried to make everything work for as broad a class of initial states as possible. But if you allow yourself to restrict your class of initial states through some sort of typicality arguments, right? Say, well, I got my state by randomly selecting it, then many of these things will thermalize also within that class of initial state. And people argue about this back and forth as to whether you should be allowed to do this or not. All right. Okay, so conclusions. This ETH, as it's now called, notion can explain how isolated quantum many-body systems thermalize just from pure quantum mechanics and using purely quantum mechanical results. And we have a large class of systems that we are very confident obey this, and even larger if we take the numerical results as valid. But you know, again, there's a community of people, both experimentalists and theorists, trying to understand how this should be. You know, what is the range of validity? What is you know, are there more precise ways to characterize these matrix elements, which is something I'm thinking about at the moment, and so. But that's the main story, and thank you for your attention.
Thank you, Mark. Questions? Start with Tathagat.
Yeah, thanks for the nice talk. I have two questions. So one is, what determines the time scale of that?
Yeah, good question. So let me see here. Where is it? Okay. So everything I've said has been extremely general, right? So when you say something very general, the downside is you don't know anything about a specific system. So the answer to the question is that the time scale is hidden in the omega dependence of this F function. And if you constructed a 2-point correlation, and actually I think I have a slide on this, so I'm trying to find the slide. Yeah, okay. So alpha, beta have morphed into I and J for no particular reason here. So we could construct a Heisenberg picture observable, and then we could consider this slightly funky 2-point thermal correlation function. So rho here is a thermal density matrix. And okay. So a sort of normal thermal correlation function would be to take trace rho A of T, A of 0. But it turns out to be slightly better for these purposes to split rho into 2 pieces and put a square root of rho between the A's, subtract off the diagonal term, and then after some manipulations, this ends up being the Fourier transform of the F function squared. Okay. So whatever time scale is we want for this 2-point correlation function is in the F function in terms of its Fourier transform. Okay, so this is now a system and observable dependent thing. Typically, observables that we're interested in will have order 1 timescales as opposed to order n timescales. So that's why I said we should think of omega as an order 1 quantity. But something people have focused on is observables that are very unusually slowly, which can identify as like hydrodynamic modes of a system. So, identifying systems where this F function has a long effective time scale is something people are interested in. But the answer to your question is the time scale is hidden in this F function. And to know the F function, we have to know a fair amount about the system.
I have one more question.
Why don't we come back to you? I think Emily, you had a question?
Yeah, thank you. So obviously your stat mech graph is time asymmetric. If the time asymmetry is not coming from an initial state restriction, where would it coming from?
It's actually time symmetric. I only drew 1/2 of it.
Okay.
Right. So if we took the graph, right, I only drew it in one direction.
Yeah.
If I drew the other direction, it would look the same.
Right.
So what's creating the time asymmetry is the initial state.
Oh, it is the initial state. Okay.
Yeah, and if we go either forward or backward in time, we will evolve towards.
So there is some initial state restriction there.
Sorry.
There is some initial state restriction there.
Yes, well, I'm deliberately picking an initial state which is far from equilibrium according to this observable, because that's the interesting thing to look at.
Right.
If we randomly picked a state somehow, we would just get a very boring curve that always lies along the thermal line.
And so I guess you have to understand that initial state, because the initial state didn't actually evolve from a equilibrium state. So you have to understand in terms of intervention or something.
Well, I'm thinking of that as I have sufficient experimental control over the system to prepare this state. Now, another thing we could do is just prepare some state and then wait for a large fluctuation.
Yeah.
And in fact, one of my papers, I try to turn this into a theory of, and show that if you did get a spontaneous large fluctuation, then it decays back either forward or backward in time according to the Kubo formula for thermal decay. So you can show things like that. But yeah, there's no fundamental time asymmetry here. The time asymmetry is created by the choice of initial state.
Right.
I'm assuming we have sufficient experimental control to create an initial state, like put all the atoms, the gas in the corner. I assume I can put them in the corner.
Great, thank you.
Other questions? Let's go back to Tathagat then.
Yeah, so the initial state you're starting from is pure state, right? It's not entangled. So I was wondering if you have entanglement, are you going to see the same thing? Or?
Yes, I mean, all that happens if you have, if you've entangled your system with something else and you traced out the something else, is that in these various formulas, like this C alpha star C beta would get replaced by a rho alpha beta, the energy eigenstate matrix elements of the initial density matrix of the system. But that this was factorizable played no role in anything I said afterward.
I have a question.
Oh, yes, go ahead, Armin.
Yeah, it was very interesting. You introduced this basic stuff to us, but I guess that you have much more to tell us. So one thing I would like to ask about, let's consider a crystal in thermodynamic equilibrium. So can we apply ETH to it so that if we will change the temperature at some point, we will have phase transition, say first order phase transition. And then how this will work applied to that case. And in principle, can you try to derive Lindemann criterion from this type of consideration, at least qualitatively?
Yeah, no, I think the answer to that is no. I mean, the first question about the crystal would be, I would need more details to know if whatever mathematical model we're using for the crystal has other conserved quantities or not. ETH will apply only if there are no other conserved quantities. So if I put sufficiently strong interactions among the electrons in the crystal, that should be true. But then ETH itself is not capable of detecting things like phase transitions. Phase transitions would show up in...
But fluctuations will go very high. And in principle, I think it should be possible because you just need to release that condition.
Yeah, well, it's a good question. I'm trying to find my matrix element formula. Where did it go? There we go. I mean, so we could ask how a phase transition shows up in this formula. One way it could show up is just in sharp, sudden changes in behavior of these functions, right? So like, if we think if this observable is an order parameter, right, then it has some expectation value that then goes to zero, say at the phase transition, and then stays zero. So that would just show up in what this function looks like.
Yeah, that's why I think there is a potential in this approach to tackle that.
Yeah, I'm just not sure this helps you tackle it, right? I think, this is a very general statement about, what needs to be true for a system to approach equilibrium. But it's so general that it doesn't tell you anything about a specific system. Whereas you want to know about, I have my system, I want to know if it has a phase transition. Yeah. Okay, well, now I need to know stuff about your system to tell you this, right? Maybe this helps. To the best of my knowledge, it doesn't help. As far as I know, no one has used this to help do that kind of calculation. But it would be great if it did.
Yeah, maybe at some point in the future, you will tell us more about it.
Yeah, I would love to tell you more about it.
Okay.
Mark, there are these classic results like the H theorem and the Poincare recurrence time and all that stuff. I imagine you've struggled over the years about sort of connecting these results. Can you tell us a little bit about if there is a relationship between your results and these sort of classic stat-mech theorems?
Well, the recurrence theorem is, it just says in a chaotic system, you will eventually come arbitrarily close to
your initial condition.
So this is really like time average equals microcanonical average, which one can find invoked in various stat-mech books. But in fact, this time average is exponentially large. If you actually say, okay, how long is it going to take to come close to this point? Well, the answer is e to the n. So this is sort of irrelevant on any scale. I do have a couple of slides on entropy, though, which might be useful. Okay, So sometimes I get the question, what about entropy? So, and one problem with entropy is that everybody loves the word coined by Clausius, and everyone likes it, so they want their thing to be entropy. So it means, in fact, there's allegedly a conversation between Shannon, who had the information entropy concept, and I think von Neumann, where Shannon asked von Neumann what he should call it. And von Neumann said, why don't you call it entropy? Nobody knows what that is anyway. I don't know if this is true or not, but okay. But we can define a class of entropies at least by saying I'm going to get my entropy by taking minus trace rho log rho of some rho. And you know, if we're going to talk about H theorems and entropy increasing, then we want our entropy to be time dependent. So then the question is, what should we choose for this matrix element? I put a tilde on it, or not, what should we choose for this density matrix? I put a tilde on it to indicate that it's not necessarily the actual quantum state of the system. It's something I'm going to make up in some way or another. And I'm going to tell you 3 different ways to make up an entropy. One is the von Neumann entropy, which is just to take the actual density matrix of the state. Well, if we're doing a pure state, this is it. And then S is very boring. It's just always 0. So this is not a very interesting. One that's popular recently is entanglement entropy of a subregion. And usually we think of the subregion as small. We don't have to think of it as small. Okay. So I have my system, and now you should think of this as like a lattice system of some kind. And I pick out a small subregion, and I take the exact quantum state, but I trace over all the degrees of freedom that live in region 2. And I'm left with something that depends only on the degrees of freedom in region 1. And I will call that my density matrix rho. Why does this not want to go? All right, there we go. A third one, which I call the Jaynes entropy, is to maximize S of t subject to constraints. And so coming back to my general presentation, I'm going to assume that we are able to track these expectation values of these observables. Now, of course, actually, we can't actually track an expectation value, but we're theorists, so we don't care. I'm going to assume we know the expectation values as a function of time. We know the energy. Rho should be normalized, and then it's a standard constrained minimization calculation to show that rho tilde is what I was talking about in terms of this generalized Gibbs ensemble. There's a temperature-like, inverse temperature-like parameter, but which could be time dependent. And then there's a similar coefficient of each of these observables. Now, these are no longer in the generalized Gibbs ensemble. These are supposed to be conserved quantities, and then these are constants. But here, they can vary in time. Okay. And so we are getting the actual expectation values from the actual quantum state, and then just encoding them in this density matrix. Okay. And this, so here I have to know what my set of observables is. And this is actually the same entropy as the entanglement entropy if my set of observables is a complete set of all the observables in region 1. And then I know everything about region 1. Okay. Now, of course, we can compare this to the thermal expectation value, in which we only allow ourselves a beta 8. So we can think of this thermal result as the same as the constrained result, but in which we don't impose the A constraint. But that means that S of t has to be less than S thermal, because we impose fewer constraints. Now, if we're in a system that thermalizes, meaning that these expectation values are all approaching their thermal value to within some fluctuations, that means that when we're at a time when that's true, these constraints are irrelevant because we would have gotten the thermal answer anyway. And so these gammas are 0 in that case. And so we get to the thermal. So if our observables are approaching thermal equilibrium in the usual way, then this entropy starts out less than the thermal entropy and approaches. Which, I think is now, what more can you ask of an entropy? This is doing everything you want it to do.
And why are you calling it Jane's entropy?
Because Ed Janes wrote a lot about foundations of StatMech so his claim was that you could understand all of StatMech just from ideas like this. And I think that wasn't quite right? You needed some more. But he's I never met him, but he's a colleague of mine, Doug Scalapino, was his student. And so I've heard stories about James from him. But he's a very interesting guy. I highly recommend his book on probability theory. It's a lot of fun. Anyway, so, this probably has some other name that I don't know, but Jane certainly used these ideas a lot, so I call it the Jane. Anyway, either this or its equivalent in the entanglement entropy with this equivalence, it gives you an entropy that I think does everything you would want an entropy to do.
Okay, I think we're out of time, so let's thank Mark again.